All right, so now it's time to level up to the next level of security. And in this lesson, we're going to cover something called hashing. Now, previously, we've already looked at encryption. So, taking the user's password and securing it using an encryption key, and then using a particular cipher method, be it a Caesar cipher or the Enigma cipher or a modern cipher method like AES, which is what we enabled on our database. No matter which way we chose, we always had a password, a key, and we ended up with some ciphertext, which will make it hard for people to be able to immediately guess what our user's password is. So for example, if we took a password like QWERTY and we used the Caesar cipher method and we decided to shift it by 1, then our encryption key is the number 1. And that creates the ciphertext where every single letter is shifted up by 1. Now, in order to decrypt this, all you have to do, as long as you know what the key is, then you can simply shift all of the ciphertext down by 1 and you end up with the original password. Now, the Caesar cipher is a very, very weak encryption method. It's incredibly easy to figure out what the original text was, even if you didn't have a key. And just to illustrate what bad things can happen when you have a weak encryption system, I'm going to tell you a story from history that tells us why we should not be using a weak encryption system. So, back in the 1500s, on this island that we now call the United Kingdom, there used to be 2 large areas. One was Scotland and the other was England. And they were ruled over by 2 queens. Scotland was ruled by Mary, Queen of Scots, who was a Catholic, and England was ruled over by Queen Elizabeth I. Now, these 2 ladies between them controlled the land that we now call the UK, but they each wanted to have more power and more land. So, what did they do? Well, Mary, Queen of Scots, who ruled over Scotland, decided to plot with her friend Lord Babington to try and assassinate Queen Elizabeth. That way, she would be the legitimate heir to both the English and Scottish throne, and it was kind of a Game of Thrones kind of situation going on back then. But in order to mobilize their forces or try to come up with some sort of secret plan, they decided to send letters to each other using ciphertext. So they came up with a system to encrypt their letters to each other, such that if it fell into the wrong hands, the subject of the letter wouldn't be revealed and they wouldn't end up being tried for treason. But the problem was that the encryption method that they used, which was a letter substitution method similar to the Caesar cipher, was a very weak form of encryption. And Queen Elizabeth had a chief decoder who ended up deciphering their letters and figuring out what their encryption key was. So he decided to take this encryption key and write a letter back to Lord Babington to try and get him to reveal all of the co-conspirators. And what was the end result of having their weak encryption system? Well, Queen Elizabeth decided to accuse Mary, Queen of Scots of treason, and hence she ended up having her head chopped off. So this is not what you want to happen to you or your website. So weak encryption systems can end up putting user passwords at risk, and your company might end up metaphorically decapitated, such as in the case of companies like TalkTalk or Equifax, where they ended up getting hacked and lost a lot of the trust of their users. Now, if you're interested in more stories like this and to learn more about cryptography and encryption, there's a really great book recommendation that I would make called The Code Book by Simon Singh. It contains stories like the one that I just told you and more. So if you're interested in this, go ahead and read more about it. Now, how can we make our password more secure? Now, at the moment, the biggest flaw in our authentication method is the fact that we need an encryption key to encrypt our passwords and decrypt our passwords. And chances are that if somebody is motivated enough to spend time and hack into your database, then it's probably not that difficult for them to also be able to get your encryption key, even if you've saved it in an environment variable or somewhere secure on your server. So how can we address this weakest link, the need for that encryption key? Well, here is where hashing comes into play. Whereas previously with encryption, we needed that encryption key, hashing takes it away and no longer requires the need for an encryption key. Well, then you might ask, well, if we don't have an encryption key, how can we decrypt our password back into plain text? Well, the secret is you don't. Let's say a user registers on our website and they enter a password to register with. We use something called a hash function to turn that password into a hash, and we store that hash in our database. Now, the problem is that hash functions are mathematical equations that are designed to make it almost impossible to go backwards. So it's almost impossible to turn a hash back into a password. How is this possible, you might ask? How is it possible that you can turn a password into a hash very quickly and easily, but make it almost impossible to turn that hash back into a password? Well, here's a question. Let me ask you, what are the factors of 377 other than 1 and 377? So basically I'm saying 377 is not a prime number. Not only can you divide 377 by 1 and 377, but there's also two other numbers that you can divide it by. Now it's your job to figure out what those numbers are. So what might you do? Well, you might divide it by 2. Okay, so that becomes 188.5. That's not a whole number, so 2 is not a factor. What if you divide it by 3? Well, that becomes 113.3 recurring, which is also not a whole number, so 3 is not a factor either. And you might go through this process for a long time, tediously, going through number by number. Well, then you might arrive at the point where you divide 377 by 13 and you end up with 29. So 13 and 29 are the answers to this question. They are the only factors of 377 other than 1 and 377. And as you can see, that process of getting to this point, of finding those two factors, took us a while, right? It wasn't that easy. But consider if I asked you a different question. If I said to you, can you multiply 13 by 29? Well, you would be able to do that really quickly and easily. It would take you almost no time at all to figure out that the answer is 377. So here is a very, very simplified version of a hash function. So going forward, multiplying 13 by 29 is really quick and easy. But going backwards, trying to get back those numbers 13 and 29, starting from 377, is very, very time consuming. So this is essentially how a hash function works. Just add a little bit more complexity and you end up with a real hash function. So they're designed to be calculated very quickly going forwards, but almost impossible to go backwards. And by almost impossible, I simply mean that using current levels of computing power, it would take far too long to make it worthwhile for the hacker. So let's say that to calculate the hash going forwards, it takes a millisecond, but to go backwards, it takes 2 years, then that hacker probably has better things to do with his time. So when a user tries to register on our website, then we ask them for the registration password, which we turn into a hash using our hash function, and then we store that hash on our database. Now, at a later point, when the user tries to log in and they type in their password, then we again hash that password that they typed in to produce a hash, and then we compare it against the hash that we have stored in our database. And if those two hashes match, then that must mean that the login password is the same as the registration password as well. And at no point in this process do we have to store their password in plain text, or are we able to reverse the process to figure out their original password. The only person who knows their password is the user themselves. Now, previously we saw that by using the Enigma machine, as long as we knew what the settings were for the Enigma machine, which is basically the encryption key, right? As long as we knew what that was, then I can decode it by setting it to the same encryption key. And we end up being able to retrieve the original text. Now, however, if I was to go and change this to a hash function instead, then you can see that when we try to decode this using the same hash function, MD5, we get the error that decoding step is not defined for hash function because you can't really go back. That's the whole point of the hash function. And this is what will make our authentication more secure. So let's go ahead and implement this in our code. So first things first, let's go ahead and install MD5, the package. And then all we need to do is just to require it and then use it to hash a particular message, or in our case, the password. So let's go over here and let's remove Mongoose encryption and remove this plugin from our user schema. And instead, we're going to require MD5. And when the user registers, instead of saving their password, which is what we got from the request.body, we're going to use our hash function, MD5, to turn that into an irreversible hash. So let's give that a go. So firstly, we're going to run our app.js and we're going to open up our website and register a new user who we'll call user@hash.com. And we will give them a password of 123456. Go ahead and hit register. Okay, success. So that means our user's been saved successfully into our database, and we can see that the email is still left as is so that we can search through it, but the password is now a hash that's been created by passing our password 123456 through that hash function MD5. And this will be impossible to reverse. We can't decrypt it, and we don't have any sort of encryption key that leaves it vulnerable. So now we need to figure out what to do with the login step. Now, the important thing that you need to remember with hashing is that when you run the hash function on the same string, the hash that's created is always going to be the same. So for example, if I decided to console log MD5 and I pass through the string 123456, then when I hit save and NodeMon reruns this app.js, you can see this is the hash that's generated. And this matches exactly with the hash that was generated here previously when I tried to register the user and hashed the password that they typed in. So this is how we're able to later then compare. So when the user tries to log in, we'll hash the password that they tried to type in using the same hash function, MD5, and then we'll compare the outcome of this with the hash that's stored in our database. And if they match, then that must mean that the initial password that they typed in must have been equal to the initial password that they registered with, because after hashing, they matched exactly. So now we're going to compare the hash that's inside our database with the hashed version of their password and see if it matches to be able to log them in. So let's hit save and let's go back to our homepage, try and log in our user@hash.com, and the password was 123456. Let's go ahead and log in. So we've managed to successfully log in because those hashes match. And this is very simply how hashing works. So now when a user decides to hack into our database, all they have are these hashes in the place of our passwords, and because of the way that hashing algorithms work, you can't reverse this back into the plain text of the original password. So that's all very well and good, and theoretically, our passwords are a lot more secure than when we simply encrypted it, because we had the vulnerability of that encryption key. As soon as somebody discovers the key, then all of our encryption was for naught. Now, hashing also comes along with its own problems though, because as soon as you come up with a problem, then some motivated hacker will come up with a solution. And in the next lesson, I'm going to show you how we can hack our users' passwords. So for all of that and more, I'll see you there.